Hello, this video is on open systems and the first law of thermodynamics. And the essential question is, how does energy move in and out of open thermodynamic systems? So hopefully when you see the name first law of thermodynamics, it strikes you that this might be something important. This might be an equation that we're going to use a lot. This is really the heart and soul of much of this entire unit. So on a test, if you get a thermodynamics question, you should be using this law, or probably you're not doing it right necessarily, right? This is the big deal in this unit, this law. So the first law of thermodynamics basically says that there are two ways that you can change a system's thermal energy. Remember that is U, the amount of thermal energy stored in the system. So the two ways that you can change it are through heat, okay, by throwing energy through conduction into the system, or by the process of work. And we've talked about work a little bit before. Remember that work is kind of a mechanical change in energy of a system that you do by pushing on an object, and we'll come back to that in just a minute. But first, the equation. So it's a really straightforward equation. Delta U, which is change in the system's thermal energy, is equal to Q plus W. It basically says those two ways are how you get a system's thermal energy to change. A reminder about this, because thermal energy is basically the sum of the kinetic energy of the particles, if you change a system's thermal energy, assuming that we are keeping the same mass in the system, which is usually the case, that means that we must be changing the average kinetic energy of the particles, which means we must be changing the particle's temperature. So anytime delta U is not zero, the object or system of gases is going to be heating up or cooling down. And by the same definition, if delta U is zero, temperature will be constant. Just in terms of sign conventions, if you have a positive delta U value, that means the system is going to increase in temperature or become warmer. And if you have a negative delta U value, it's going to get colder. So you can make your system's thermal energy change, increase or decrease by heat or work, or a combination of them. Okay, so quick little refresher that heat, which we've talked about in previous videos, is the variable Q, and it's the thermal energy that's moving in or out of a system via conduction from contact with some other system. We measure heat in joules. So if you were talking about the system of that waffle, well, you know, it's going to absorb heat from the metal plates of the waffle iron, and that will increase the thermal energy of the waffle. It's going to heat up. Those eggs could be absorbing thermal energy through conduction through their shell, right? And that's going to increase the temperature of them. Or your toast is probably absorbing energy through radiation, but also potentially through some conduction by the toaster itself getting warm. So that's the heat. Hopefully this makes sense, but if you have a positive Q value, the thermal energy tends to increase, and a negative thermal Q value tends to decrease it, pending what's going on with that other variable, which is work, which we'll talk about in the next slide. So we've mentioned work in a review video before, but a reminder that work is the variable W. And the classic physics equation, which you'll find in your equation sheet, is that work is equal to a force acting over a distance, or a force multiplied by the distance through which that force acts. But for gases, we have a harder time measuring forces than we do pressure. We can use pressure gauges. It's hard to measure the force from a gas because the gas just moves around. So we're going to rewrite this equation. We're going to reimagine work, right? Work was equal to force times distance, but we know that pressure is force over area. So another way to say force is pressure times area. So I'm going to replace the force with the pressure times the area in that equation. And since we know that volume is the area of an object multiplied by the distance or the length of that object, we can substitute out a volume for the A delta D that would be left in that equation after we put in the force. So if you didn't follow that whole derivation, I'm happy to go through it in class again. but we end up with this equation right here, which is on your equation sheet, which is for a gas system, work is equal to negative P times delta V. This is the same as F delta D, it's just for gases. So in this picture that I've shown here, right, if you measure the pressure of this gas and you change its volume, the work is going to be equal to the pressure of the gas multiplied by the amount of volume change that that sample undergoes. You may have noticed the negative sign in that equation. What that tells me is that when the sample's volume is decreasing, so when delta V is negative, when we're going from a big sample to a small sample, we're going to end up with a positive work. We're going to define this as work on the system. So in other words, when you take a sample of gas and you squish it, it's going to increase the thermal energy of the gas. And of course, the flip side is going to be true as well. If you take a sample of gas or of anything really, and you stretch it out, you expand it, that's going to be negative work, which would cause the thermal energy in general to go down. We call that an expansion when a system's volume is increasing. So that negative sign just helps us kind of keep track of whether we have positive work being done when things are squished or negative work being done when things are expanded. You're thinking to yourself a little bit, why? Why does squishing a gas cause its internal energy or its temperature to change? Like, you know, if I squeeze this gas, am I really heating it up inside my hand or cooling it down? Well, it's helpful to go back to the kinetic theory perspective and think about what's happening from the perspective of those tiny little molecules. So imagine that we have this container, and imagine it's kind of like tennis racket. The container itself is like a spongy tennis racket, and it's being bombarded all the time by the tennis balls, which are like the molecules inside the container. If those walls are static, which means they're just standing still, the molecules are going to bounce off at the same speed they came in at, perfectly elastic. This is what we did in the last unit. Pretty much all the energy stays in the system if the walls are standing still. However, if I take those walls and I actively move them towards the molecules, it's just like a tennis racket actively moving towards the ball. And if you've ever hit a ball with a tennis racket, you know that by actively moving towards the molecules, you can actually transfer energy from the walls to the molecules. You can actually force them to gain energy from the collision of the walls with the molecules. And because that's a transfer of energy into the system, it's going to increase the temperature and the internal energy of the system. The flip side's a little bit harder to imagine, but if we allow the balls to push the wall outwards, okay, then every time they do that, every time the wall moves outwards because of a collision with it, the balls are going to lose some energy as well. It's being transferred into the wall. If you've ever like caught something, you know, a ball hit it and you kind of like cushioned it, you'll know that the ball doesn't bounce off as vigorously than it does if the wall is standing still, or if the wall is moving towards it. If the wall is allowed to move backwards, then it actually sucks some of the energy out of the ball. And in terms of kinetic theory, that means that the molecules are losing energy and going to get colder. There's also a third case where the wall is just removed entirely. So we're not squishing in or expanding out with the gas, we're just removing the wall. And if we do that, then the molecules inside the system are not gaining or losing energy to that wall, and we're going to keep a constant temperature. This is called a free expansion. So when we played around with that simulation last time, when you change the volume, it was doing it with a free expansion model where it was like the volume was just changing, but the particles were not actively involved in the changing of the volume. So I'm actually going to keep this a pretty short video because I think we really need to practice with this material and explore it a little bit from a hands-on and a equation perspective, but I did want to at least introduce it briefly. So the topic, if you wanted to revisit it in your notes, how does energy move in and out of open thermodynamic systems? So hopefully you know now through heat or work, and how do we calculate work for a system of gases. Thanks for watching.